Hey students, welcome to Sustainable Energy. I'm Rudi Schlaf, a professor at the Electrical Engineering Department at USF. This is part 3 of the energy storage segment. In this segment we will discuss electrodynamic storage at the example of superconducting magnetic energy storage. Then we will discuss mechanical storage with the subtopics of hydroelectric, compressed air, and flywheel storage. And then we will discuss feasibility and applicability of the various energy storage technologies. All the methods we discussed so far to store electrical energy had to do with storing this energy as potential energy of electrons. We took them from a low energy level and then the generator moved them up to a high energy level, and the storage medium tried to keep the electrons at this high level until the time would come when this energy was needed. Another way to store electrical energy is through electrodynamic energy storage. Here we store a current in a coil, and so if we connect a power source to a coil, then the current inside that coil rises slowly over time and reaches a final value. So it follows this curve. The reason why this current doesn't come on immediately like it would if we just hooked up a resistor instead of this inductor is that inside this coil a magnetic field is induced by the current, and this magnetic field creates a voltage that pushes against this current. So the voltage that's induced in this inductor is opposite to the voltage of the power source that we connected to that inductor. So during this period, as the magnetic field establishes itself inside the inductor, the current is counteracted by a current that is produced by this voltage that is created by the magnetic field that is induced. So this voltage goes to zero at the moment when the current reaches its maximum and constant value. At that point, we don't have to perform work anymore to get this current going inside the inductor. But the work against this voltage that was expended during ramping the current up, this work is now stored as energy in the magnetic field that is inside the inductor. This method can be used to store electrical energy inside a coil, an inductor. If you think of it, this is a wire and there's a current flowing. Of course, at room temperature in a normal inductor, there is resistance in this wire, and that means if we wouldn't keep pushing with the power source, the current would simply cease after a while once all the energy has dissipated as heat from this wire because of the resistance. But if we would use a superconductive conductor as this coil, then one can push a current in and ramp it up to its maximum value and then disconnect the power source from the inductor and simply make a short circuit across this coil, and the current would keep going infinitely inside the inductor because of its superconductive properties where the resistance is zero. The issue, of course, with this is that one needs to keep this inductor at a low temperature because superconductivity can only be achieved at cryogenic temperatures. Once the energy is needed, all we have to do is connect a load instead of this power source to the inductor, and the current will pass through the load and work can be done inside the load with that energy. Here's the formula for energy in a coil. We have 1/2 times the inductance times the current squared. So this is the current after it became constant. And once we know the inductance, we can calculate the energy that is in the coil. The inductance of a coil is calculated multiplying the permeability of free space with the number of wire turns squared times the area of the cross section through the wire turns divided by the length of the coil. So it's really the number of turns per length that is the important factor in a coil that determines the amount of energy that can be stored in it. Electrodynamic energy storage is only possible if we can make coils that have no resistance. Otherwise, we would constantly lose energy as heat to the environment, and the storage could be only for the very short term. Wires that have no resistance can be made from superconductors. Superconductors are materials that at a certain transition temperature lose their resistance. Here you see the dependence of the resistance on the temperature for yttrium, barium, copper oxide. And this material, like all conductors, shows the typical reduction of the resistance as the temperature is lowered. This is a result of the reduction of lattice vibrations, and that is common to all conductors. But in superconductors, at the transition temperature, a certain drop to zero occurs. In the case of yttrium, barium, copper oxide, this is at 93 Kelvin. This material can be used with liquid nitrogen cooling, and it can be superconducting. This is a so-called high-temperature superconductor, and that makes it different from the classic superconductors that were discovered first, so-called type 1 metals. They have typically transition temperatures in the single-digit Kelvin range, and they require liquid helium for cooling to observe this effect. This makes them prohibitively expensive for industrial applications, and that is why high-temperature superconductors are a very active field of research right now, because if one could make such storage devices with only nitrogen cooling, it would become much more feasible as a large-scale application. The basic layout of a superconducting magnetic energy storage facility is fairly simple. We come in from the grid with AC, we have rectification, and then a DC current is stored in the superconducting coil. Of course, there needs to be a refrigerator that keeps the coil below the transition temperature of the superconductor. One issue of current high-temperature superconductors is that they can only have a low current density, and this means that the energy density of the superconducting magnetic energy storage facilities right now can only be fairly low. The great advantage of these facilities is that they can have a very high power output, because the current is already in the coil, and by connecting a load to it, one can extract this current in a very short time frame. So the main uses that are projected right now for such facilities are in system stability applications and pulsed power. So if one needs a lot of power over a very short period of time, this is an interesting application. This shows an artist's rendering of a superconducting magnetic energy storage facility. The superconducting coil is buried underground. The reason for that is, on one hand, that these coils need strong mechanical support because of the considerable Lorentz force that acts on the coil when the current is circulating in it. The other reason is that the effect of strong magnetic fields on living organisms is not fully understood yet, and so it is best to keep these coils out of reach. In the next few slides I will talk about mechanical storage schemes. The by far most used technology is pumped storage. Here you see a schematic of the Ludington Pumped Storage Generation Station on Lake Michigan. It has 1.8 gigawatt output power, and over the next 10 years or so they will increase it to 2.1 gigawatt. So the way this works is we have Lake Michigan, and there are reversible pump turbines. And during times of high electricity production but low use, these nearby nuclear power plants drive these pump turbines as pumps, and water is being elevated into this reservoir, so we gain this amount of potential energy, gravitational potential energy. During times of need, the water is released back through the pump turbines, which are operated as turbines, and electricity is generated. It's interesting to know that the total pumped storage capacity in the US is 21.5 gigawatts at this point, and this represents about 2.5% of the US generating capacity. So only a very small part of the generating capacity is backed up by storage. Here you see an aerial photo of the Ludington Pumped Storage Facility. The water in and outflow is down here. This is where the pump generating units are, and this is the reservoir. It takes advantage of a natural cliff that elevates the adjacent land area next to the lake. That enables this reservoir to be at a suitable height above the generators. It's interesting to note that the generation capacity of this facility is the equivalent of about 2 major power plants, 1.8 gigawatts. Another physical way to store energy is via compressed air energy storage, CAES. This storage technology is based on the ideal gas equation. If you recall, the energy in a gas can either be defined through macroscopic quantities, the pressure and the volume. So if we multiply pressure and the volume of a gas, then we know the kinetic energy that is in the gas. That is equated in this equation with the number of moles of molecules times the universal gas constant times the temperature. So what we're doing on this side is we're simply adding up the energy of all the particles that are in the gas. So it's obvious that we can store energy in a volume by increasing the pressure. So one can take a compressor and pump more gas into the volume, and that increases the energy that is inside this volume. In terms of number of molecules at a certain temperature, it means that we simply increase the number of molecules in that volume, and of course that gives us a higher energy that is inside the volume. So no matter how you look at it, by putting more molecules inside a given volume, we can store energy. Now, the ideal gas equation is called ideal because it omits the fact that molecules attract each other. Two molecules, even if they are electrically neutral, will still exert an attractive force on each other because of their polarization. This is called van der Waals forces. And that means that molecules that are far apart from each other have a high potential energy, and if we let them come close to each other, if we let them attract each other, then this potential energy is converted into kinetic energy. So they accelerate towards each other, and potential energy is converted into kinetic energy of the molecules. In other words, the potential energy is converted to heat in the gas. So as we pump more molecules into this volume, we decrease the distance between the molecules. And that means that their potential energy is lower, and if we prevent energy exchange with the environment, so in practical terms, if the volume is insulated against heat exchange with the environment, then we get an increase in the kinetic energy because we lower the potential energy, and that increases the temperature. In any practical compression scheme, as we raise the pressure, the temperature goes up inside the volume. This temperature increase is of course part of the energy that is stored inside the gas volume. And if the gas volume is not insulated, if the heat is dissipated to the environment and the volume stays at the temperature of the environment, then we're losing this energy to the environment, and that reduces the efficiency of this energy storage process. So there are essentially two principal ways to operate compressed air energy storage. One is adiabatic. That means we really insulate the volume and make sure that the heat is stored together with the compressed air. The other principal way to deal with this heat build-up during the compression process is to do it in an isothermal way. Isothermal means with constant temperature. And what we do with the heat in this case is we store it in the environment that surrounds the container where we press the gas in. So here, in difference to the adiabatic approach, where we try to insulate the container as good as we can to keep the heat inside together with the compressed air, in the isothermal case, we actually try to facilitate the heat exchange with the environment. And imagine now what happens. As we compress air into the isothermal container, the heat builds up, but if the
heat exchange with the environment is efficient, the heat will immediately go into the environment because the environment has a lower temperature. And you know now that heat can only be exchanged towards an object that has a lower temperature. And so that the heat immediately goes into the environment, and we continue to compress air into the storage container, and all the heat that builds up immediately goes into the environment. The consequence here is that the pressure in the container is lower per number of molecules we have in there because the temperature is lower, because this here needs to be equal to P times V. And that means that we essentially only have the kinetic energy that's in the gas molecules in the first place as we push them into the container, and the heat that comes from their potential energy reduction is in the environment at this point. Now, what happens if we reverse this process? So now it's time to draw from the energy storage and get some energy back out. So in the adiabatic case, we let the air escape into a turbine. And of course, what happens in the adiabatic case is the heat is lowered along with reducing the pressure. Because as we let molecules escape, the number of molecules is reduced inside the volume and their distance increases between each other, and that means that we build up potential energy again, and that costs us some of the heat. So the heat is reduced inside the adiabatic vessel as the pressure is lowered. In the isothermal case, the gas is escaping from the container, and of course, the temperature also will go down in the container. This is what you experience when you have a spray can and you spray a lot with it, and you can tell that the spray can gets cold. Of course, the environment, your hand that holds the spray can, is warmer, and so you are actually transferring heat into the spray can, and this is the isothermal case more or less. In this case, the heat that was initially put out into the environment is now coming back into the container as the gas is being extracted. This process only works well if we do it really, really slow. Otherwise, like in the case of the spray can, it actually gets cold, and that means that the spray can loses pressure on the inside, and so the paint is not coming out as effectively as it would if the temperature was higher. So when it comes to releasing energy, we want to funnel that heat from the environment through our pressurized container in order to get all the energy back. But this we can only do if we do it really slow, because we have to give that energy some time to make it from the environment into the container and keep the temperature constant. So the isothermal case, while sounding pretty interesting, is not a practical case because we would have very low power in this process, right? Power is energy per time, and since we could extract the energy efficiently only at a very slow pace, we would have a very low power in this application, so this is not practical. So a practical case clearly is adiabatic, but we would have to come up with some really good insulation that would long-term keep the temperature high inside the storage container. Otherwise, this would only be a very short-term storage, because we would lose gradually heat to the environment, which would make the storage less efficient. In practical terms, neither of these two approaches are considered advantageous, and so in storage plants, a process that is called diabatic is used. Diabatic means we have heat exchange, but we don't keep the temperature constant, at least not during retrieval of the energy. The way this works is by using a heat exchanger that during the compression process directly removes the heat as it builds up after the compressor. That makes it easier to squeeze the gas into the storage volume, so we don't have to work against the building up heat, and that saves energy in the compressor, and so we get, at least during the storage process, a fairly high efficiency. When the air is released, of course, the temperature is going down inside the storage container, and this is where we lose the heat energy. That makes it different from the isothermal process, because here we do it very slow, and so the environment has time to give energy back. In this process we are in a hurry because we want a high power output, and therefore we accept a temperature lowering. This process is typically coupled with a gas-fired turbine, where the compressed air replaces the need to pre-compress the air intake of that turbine. Since this costs energy, the gas turbine becomes more efficient, And this is the moment when we get the energy back from the compressed air storage. In difference to pumped hydro, there are only 2 compressed air energy storage facilities worldwide. One is in Germany in Hunddorf and the other one is in Alabama in the US. The one shown here is the one in Germany. There is a paper that reviews 20 years of operation of this plant. This is where these figures were taken from. This is an aerial shot of the plant, so you see here the gas-fired power plant and the 2 wellheads for those caverns where the compressed air is stored. Here's the schematic layout of the power plant. The 2 caverns with the compressed air. Here's the generator, this is the turbine, and you see that the air from the caverns can be fed into the turbines. So here this is where we get the pre-compression benefit. On the other hand, the generator can be reversed as a pump, and so we can feed air into the caverns to store energy. Here are some specs of the Hunddorf plant. The rated output is 290 megawatt. It can hold that for 3 hours. That is about at the level of a third of a major power plant. So this is really massive storage, and it could really stand in for a big wind farm in those times when there is no wind. It takes 12 hours to load the storage, to pump the air in. The storage volume is a cube of 67.7 meters length. The pressure levels inside range from atmospheric pressure to up to 70 bar. Here you see 3 graphs that show the pressure, the temperature and the airflow as the pressure is released from the cavern of the Hunddorf plant. We start out at 75 bar pressure in the cavern, and then as the air is released, the pressure goes down. At the same time, you see that the temperature is also dropping. So this is this effect where we convert kinetic energy to potential energy, and this helps to drop the pressure faster, and this is where energy loss occurs. In the airflow graph, you can see that the airflow can be kept constant for a few hours, and then we enter the reserve phase of the storage where the airflow is dropping because the pressure is too low already. Here's a study of the feasibility of compressed air energy storage. The good part is that large areas of the US are potential sites for this type of storage, and they are located where there is wind. So this might make it an interesting backup for wind farms. When it comes to the storage efficiency of compressed air energy storage, the diabatic plants have only 45% or less storage efficiency. This is because we lose the heat from the compressed air. If one would implement adiabatic plants where the heat is stored through insulation, one could achieve a storage efficiency of 70%. For comparison, pumped hydro can achieve a storage efficiency of about 80%. So we see again that every time we convert energy from one type into another, we lose energy as heat to the environment, which lowers the efficiency. The last physical storage technology that I want to discuss in this segment are flywheel batteries. Flywheel batteries are based on rotating cylinders. Energy is stored by using an electrical motor that accelerates this flywheel and gives it a certain energy. The rotational energy is given by 1/2 times the moment of inertia of the cylinder times the angular velocity, so how fast it spins. The moment of inertia of this cylinder is 1/2 times its mass times its radius. And so you see that the gravimetric energy density can only be increased by increasing the rotational speed, because the mass is linear in this energy equation. So by increasing the mass, we cannot get a higher energy density. In practical terms, this means because centrifugal forces can blow up the cylinder. If one wants to increase the energy density, typically the angular velocity is ramped up at the expense of the mass. It's interesting to note that the energy storage efficiency of these flywheels is 95% or better depending on the bearings. One can use magnetically levitated bearings which reduce the friction of these flywheels quite dramatically. Further steps can be taken by putting them into an evacuated container to reduce the friction between the flywheel and the surrounding air. Another interesting fact about flywheels is that the power output, in difference to the energy density, is linked to the mass, because we need to increase the mass of the cylinder if we want to increase the power, which means how much energy we can dispense per time from this flywheel. The last few slides I want to use to examine how the various energy storage technologies that we discussed compare in their key parameters. This slide discusses the power rating of the various energy storage methods. On the y-axis we have the discharge time at the rated power, so how long can they output power before they are depleted, and on the x-axis we have the absolute system power rating. The winners in both fields are pumped hydro and compressed air, simply because they are massive, large-scale storage technologies, so they have a higher power output and can supply this power for many hours before they are empty. Depending on the properties of these storage technologies, they are used in different applications. Pumped hydro and compressed air are in energy management, so they really back up power plants in case of failure or in case of intermittence. Then the storage technologies that have only a low discharge time, but they have a high system power rating in a small space typically, they are being used for power quality and uninterruptible power supply purposes. So they are short-term, high-output storage technologies that can be deployed across the grid. Batteries, on the other hand, are in between, and they are usually used in mobile applications. This graph examines the efficiency of the various energy storage types and their lifetime. So how many times can we charge and discharge them before major service needs to occur. The y-axis shows the efficiency, and so we see that the technologies with the highest cycles and the highest efficiency are pumped hydro, flywheels, capacitors, and lithium-ion batteries. When it comes to lifetime, one can generalize that batteries typically have a poor lifetime and physical storage technologies have a high lifetime. The reason for that is the chemistry that happens in batteries. Chemical reactions are never 100%, and that means that over time unwanted reaction products build up, and this leads to the reduced lifetime of batteries. An interesting comparison is of course also how expensive the various technologies are. Here we have the capital cost per unit power on the x-axis in dollars per kilowatt, and on the y-axis we have capital cost per unit energy in dollars per kilowatt hour. Now, this looks like all the storage technologies are fairly similar, but please note that we have here logarithmic scales. And so this means that there are quite significant differences between the technologies. For example, high power supercapacitors, they have a very high cost per energy, but a fairly low cost per unit power. So these are clearly a good choice for short-term power regulation. If one wants a very low cost per unit energy, then clearly the large-scale storage technologies, pumped hydro and compressed air, are interesting. Lithium-ion batteries, they are expensive on both counts, but of course they have a high energy density relative to other storage technologies, and that means that they are interesting for mobile applications despite the high price. So again, depending on the application, one needs to look closely which of the storage technologies are the most practical and cost efficient. This brings us to the summary of the energy storage segment. I think we can say that physical technologies mainly hydro and compressed air, seem to have the best parameters for large-scale deployment. There's low cost, long-lasting, large energy capacity, high power output, and they are also fairly simple technologies. They have everything it takes to smoothen out the intermittence of renewable energy sources. Compressed air has a large expansion potential because there are many suitable sites across the US. But the issue is that there is a relatively low efficiency associated with this technology. When it comes to chemical and capacitor-based technologies that directly store electricity, they have issues with regard to longevity and materials availability, but they are currently the only real option for mobile applications. When it comes to the hydrogen economy, I think we can say that there are many issues that need to be resolved. There are production issues, storage issues, and efficiency challenges. Production could be done via electrolysis with renewable energy, namely wind power and solar power. However, storage suffers from low volumetric density, and that causes the need for large and heavy tanks. But I think the biggest issue with hydrogen is that the hydrogen cycle has a very low overall energy efficiency because of the many conversion steps. Remember, we have to go from electricity through electrolysis, which has a 70% efficiency. Then we store the hydrogen. There we are at less than 50% currently. And then we have the fuel cell to make electricity again, which runs at 40% efficiency. So if we multiply 0.7 times 0.5 times 0.4, we end up with 14% storage efficiency. That means that we're losing 86% of the energy simply by making hydrogen and storing it before we can use it.
This concludes part 3 of the energy storage segment. Thanks for watching.